So this notebook is on an intro to machine learning. So why do we care about machine learning? Well, basically, if we had a model of the world, like a perfect simulation, we'd be able to solve all kinds of problems. We'd be able to do things like simulate what the weather would be like tomorrow, or what drugs would be effective for treating diseases, etc. So basically, building machines which can represent, which can model the world, and that is make accurate predictions about it. That's the whole goal of AI, so that we can use that model to test out different things and make accurate predictions about the world and everything going on within it. But we can't have perfect models because the world is too complex. So we have to build predictive models, and that's basically what AI is all about these days. So, for example, we want to do things like this. So we want to have some input and make a prediction of where is the object that we care about in the image, that kind of thing. So that's an example of object detection. Another thing we could predict is what are the words from some audio sound wave. Another kind of thing we could predict is from some tabular data, what is missing values in the tabular data. So it's all about predicting some useful output that we care about from some input. And all kind of problems can be formulated in this way. Just giving a few examples here. We're basically going to walk through how we do that now. So almost all machine learning algorithms consist of four things. That is the data, the model, a criterion, and an optimizer. And we're going to walk through each of those step by step in this notebook. Just as a side note quickly, probably worth knowing from the off, there are basically three types of machine learning. Unsupervised learning is the paradigm where you don't have any labels, you just have the raw inputs. So you just have a huge image data set, but no label specifying what's in the image or what the image is of. Reinforcement learning is basically where you have some system that interacts with an environment, and then because it interacts with the environment changes and it perceives some new state of the environment, and then it has to continue to act to perform goals and perform tasks and achieve goals. Supervised learning is what we're going to start with in basically the first of all these tutorials, and that's where we have both inputs and outputs for every example in our data set. And so we're basically going to learn that mapping from maybe input image to output classification of what's in the image. We'll just go over these synonyms as well. Inputs, the same thing, you might call them features. So if our input is an image, you might say the features are the pixels of that image. The outputs, maybe they're the classification of what's in this image. Is it a dog or a cat? And that's the same thing as the labels. We're going to talk about the criterion later, and that's also called a loss function, cost function, error function. We'll get onto that. So basically, firstly, to start with, what is the data? That's what we want to know. And this really defines what problem we're solving. So in general, we're going to have a data set, which I've written as a huge X here. And what that might consist of is a bunch of different examples. So the data set is full of examples in the data set. And the data set is full of examples. This one, I've given an example of a data set of people. So the first one is me, and the last one is another person. And each of these different examples, the example inputs have an index. So this is a data set of m different people from 1 to m. And then each of those individual examples might be a collection of features about that example. So if we take me in the data set, I might have all these different things recorded about me. So maybe the first feature, this x1, example I, so here I would be 1, this would be this example, that example I, example 1 has this feature 1 all the way up to feature n. So we've got n different features about this example, and maybe there's something like age, height, gender, shoe size, just features of this individual. We'll have all of those features for every single one of our examples in the data set. So this X will actually be a big matrix with n rows and m columns, as I've drawn here. So n is the number of features, m is the number of examples in the data set. And then because we're doing supervised learning, we're going to have an accompanying set of labels in the data set. And so for each of these individual examples, we're going to have a label, maybe that's like predicted how much they earn or something like that. But this is basically the setup for, we can do this for all kind of different problems. And we're basically just going to try and map, we're going to find some mathematical function which takes in an x and gives out a y to make accurate predictions for any given x, any given input example. So we'll start off by just, we're going to make this function and it's going to make us some linear data. It's going to make a straight line, okay? So we've been given these ground truth weights and biases. So what we're going to do is we're going to have a straight line which has a certain weight, that is a certain slope, which weights how important the input is. And it's also going to have a certain bias, this b, which is the intercept of that slope with the axis. So that controls where does it cross the y-axis. So to start this off, we'll just get a range of numbers, which are going to be the input values which we take. So we'll use numpy, I've imported as np.linspace. So we're going to get m linearly spaced out examples between, let's say, -1 and 1. And so then this m goes there. That's how many examples that we want. And then we're going to have some output from this. So this y is going to be, well, we're going to take the ground truth weight and multiply that by x, and then add the ground truth bias b. And then we're just going to add some random noise of size m. Each of these will be vectors. You can print them out if you want. And then we're going to add this vector of random noise just to make it so it's not perfectly along that line. It's kind of spread out around it. Then we're going to return those features and labels of our data set. And then we're going to use this function over in here just to plot them. So if we run that, that's what our data set looks like. Inputs and the outputs. And we're going to try and learn some function which maps from this input to this output. So the second part, the second ingredient to making machine learning systems is model. And this is really how can we make predictions? What is the mathematical function which represents the transformation from our input to our output? So for example, we might have a model which takes in some x and returns some y. This would be an example of a linear model. This is just the equation for a straight line with a weight of 2 and a bias of 3. So a gradient of 2 and an intercept of 3. So the general form, our output is some weight multiplied by our input plus a bias. Same thing here. So the weight really controls like how much does the input affect the output, and the bias specifies where does this, if the input is 0, what value should I output anyway? For example, maybe our input features, maybe that's like the size of maybe it's the number of taps in a house, and maybe in one house there's no taps, but there's still a house, and we're trying to predict the price of it, so it still has some value. So this x number of taps would be 0, b would be non-zero, and this is say even though the house has no taps here, the bias is some non-zero value, so our output is non-zero because that plot of land, that house is worth a little something, even if it doesn't have any taps. So we're going to make this model, and we're going to make that class. It's going to be called linear hypothesis because this is a linear model which is going to make a hypothesis about what the output is. So it's going to make a prediction of that y. So when we start it, what do we want to do? So when we create an instance of this class, we're going to initialize that, and what we're going to do with that is we're going to firstly randomly initialize both the weight and the bias, just to totally arbitrary values, and then we'll update them later to make the model better. So we're going to start by saying random w and b. So we'll say np.random.rand, and then np.random.rand, or you could do rand n, and then we're going to we're going to define this this call method here. So this specifies, so this init specifies what happens when I say my model is equal to linear hypothesis, like that. When we do that, it creates an instance of our class and it will run this initializer. When we, now what we could do is we can call the class with some input x, and then that will, and this function here, this double underscore call double underscore, that defines when we do that. So when we call our model with some x, we want to produce some y, some prediction, okay? So what we're going to do is we're going to just use our model, which looks like this. It's a linear model. So we're going to say self.w. So we'll get the weight, which we initialize randomly when we create this instance of the class, multiply that by the input x to this function, and then add the current bias, and then we'll return that. So that's just implementing that function there, which is the equation for a straight line. And then what we're going to do later is we're going to basically test how good are these parameters, and then we're going to choose better ones and see if they're any better. And we want to be able to update the parameters of our model. So what we're going to have is this method of this class called update params, which we can call with new weights and new biases. And what that's going to do is it's going to set the model's weight to the new weight you've passed in, and set the model's bias to the new bias which you passed in. Okay, so I need to do that. Then we will create an instance of our model by doing this. So we'll create that instance of that linear hypothesis, and then we will make a prediction on our inputs x, and we'll do that by saying h of x. So that's hypothesis of x, and that gives us this. We also printed here what are the initial weights and the biases of the model. So you can see it's got these two randomly initialized values. It takes in these inputs and it makes these predictions for the outputs. So we take in x, return y, take in our features, return predicted labels, take in inputs, return predicted outputs. Cool. So now we can use that model, evaluate it for every different example that we've got on our data set, see how good it looks at the moment. So that's just a helper function to plot our hypothesis against our data. And when we run that, it looks like this. So there is our true data. And here is our current model with the randomly initialized parameters, which are no good to start with. So now we'll talk about the third part, the criterion, which is basically a measure of how bad our model is. And as I said earlier, the criterion can also be referred to as a loss function, a cost function, an error function, all different kinds of things. So if you hear any of those, it just means what we're going to talk about here. Now, the first and most simple loss function we're going to talk about is the mean squared error loss. So what this does is it's used for when you're predicting continuous output values like we are here. We're just predicting some continuous label. And what it does is exactly what it says. It takes the error between your prediction and your label. For every example, it squares it, so it makes all of them positive, and then it takes the mean of all of them and produces a single number. And this single number, the whole point of a criterion, of a loss function, is the fact that the number which it returns is meant to be a measure of how bad your model is. So ideally, when your model is doing as best as it possibly can, this criterion will return a low as possible value as it can, or maybe 0, or maybe lower. So yeah, and this is the equation for that. Like I said, we're just taking the predictions that we've made, subtracting the real label. So y hat are our predictions and y are our actual label. We're going to take the difference between those two. So if our y hat is not exactly equal to y, then the difference will be some non-zero number. Maybe it's positive. It will be positive in the case which we've over-predicted, if this is higher than the label, and it will be negative if our prediction is less than the actual label. But whether it's positive or negative, in either direction, we want as this error gets bigger, whether it gets more positive or more negative, we want that to increase our loss. So we want the value of this difference to be positive. And so that's why we square it. That's part of the reason. And then we're just going to square all those differences and sum them up and then take the average of them by dividing by the number of them, which is m. So there's m examples in this data set. So how are we going to do that? We're going to define our loss. So we're going to define our mean squared error loss. Well, what's the error? Firstly, that's going to be our prediction. Take away our labels. Then we're going to square that. So we'll use numpy square the errors to get our squared errors, and then we'll do np.mean mean squared error. Cool, and then we'll calculate the cost. So let's just be squared. Oh, my bad. Cool, so there's our loss for our randomly initialized model, okay? So that's how bad it is. That single number, again, is meant to be a measure of how bad the model is currently doing. So what we want to do, I'm sure you can guess, is we want to try out different weights and biases, different slopes and intercepts of our straight line, and try and minimize this value. So we want to minimize the mean squared error for our model when it makes predictions on the data set, which we have. So now we can discuss the fourth part, the optimizer, which tells us how are we going to improve our model. Most machine learning models are parametric, which means that the function they represent depends on their parameters. So in our case, it depends on the weight and the bias. These different optimizers, we can have all kinds of different optimizers. They're meant to improve our models using all kinds of different algorithms to improve each of those parameters so they better represent the input-output relationship, which the data set shows empirically. So in this notebook, we're just going to implement some really fundamental optimization techniques. First one, random search. So I'll go through that now, and then grid search. So random search is basically, we set out a range of examples which we want to try out for our weights and our biases, so somewhere in this region, and then we're just going to randomly sample values of each of those parameters from that space, try them out with our model, and see how well they perform, okay? So we're going to define this function which performs a random search. So the first thing we're going to do is we're going to say, okay, well, what's the best weight so far? Well, we haven't tried anything so far, so let's just say it's none. There is no best weight or best bias so far. What's the lowest cost? Well, we haven't got one yet, so we want anything that we try in the future to be better than this. So we can actually make infinity the lowest cost that we've experienced so far. Now, for I in range n samples. So this is, we're going to pass this parameter which tells it how many different samples should it make. Then we'll just use numpy to randomly sample weight and a bias from somewhere within this range, which is specified by this limit, which is a keyword argument to this function, which I've initialized by default as 7. So it's going to look in somewhere in the range from -7 to +7, choose a random value for both the weights and the biases, and they're the ones we're going to try out. So how do we try them out? Well, we're going to use some method of our model H. So what did our model have again? So our model was an instance of linear hypothesis which had these 3 different methods. Which of these is going to update the parameters? That's exactly this one. So we're just going to pass to the update parameters method the new weights and the new biases which we want the model to set its weights and biases to. Okay, so now we'll just do that. So update underscore params. We'll update with the new weight and the new bias, and then we'll make a new prediction. So then now we've updated the model's weights, we can make a prediction for our input values, and then we'll calculate the loss using that function that we just implemented, L. So L takes in our predictions and our labels and compares them. So we got this y hat, that's our predictions, and we have our labels, which are the capital Y, which we defined above. And now, okay, so how does grid search work, right? We're not just going to try out different values, but we're going to keep track of what's the best one. So how are we measuring what's the best? We're using the cost. So we'll say if the cost is less than the lowest cost, which we initialize as infinite. So if the cost is better than anything we've seen so far, then we'll set the lowest cost equal to this cost. So that will be what all the future samples are compared to see if they perform better or worse. And then we'll set the best weights to, well, the weight which we just tried. So B, and then we'll actually, given the comment, we can do h.w for the best weights. And then we can do h.b for the best bias. So they're the ones which we currently set in the model. It's the same as W and B in this case. Okay, and then it's just going to keep trying that for however many samples we say. It's going to keep track of the best weights, best bias, and the lowest cost. Then it's going to print the lowest cost with the best weights and best bias. Then it's going to return us those best weights and the best bias. So how do we actually use that random search? Well, we'll just call it like this. We'll say do 100 samples. We haven't given it a limit because we don't need to, because it's already by default 7. And then once this has done those 100 samples, so chosen 100 different random pairs of parameters in this space, then it will return us the best weights and best bias. And then we need to make sure that once we've got them, we actually update our model to use them, because if we don't, it will just be using the last one which it tried, which might not necessarily be the best one. So we'll do, again, update underscore params with the best weights and the best bias. We'll run that. Random search not defined, I haven't run that. Cool, now that's looking better. That looks like our model is somewhat getting better at representing the input-output relationship which we want. Cool, so that was the first piece of optimization we've done. Really simple, fundamental optimization algorithm, but it seems to be working. So let's talk about what happened. At least it got close to fitting our data. And why doesn't it get closer even if we sample more? So let's try and do this for 1,000. Still doesn't look any better. What about 10,000? Run it, still doesn't look any better. Why is that? Well, it's because why I've initialized it as 7 is just to highlight this point, which we don't know where exactly, or we might not know exactly where our best parameterization lies. Maybe it's not in the range from -7 to 7, which is what we're searching for using this random search. So maybe we have no idea about where the best parameters would be, and so we might put some bias on the optimization algorithm which says, yeah, you should search this region, but if they're not in there, then the optimization algorithm won't work and it won't be able to get as close as it could. Let's try it with, so now we can pass in a limit argument, let's say it equals 10. And we'll run that, and then look at that. That seems to model it a bit better, at least. Cool. But yeah, have these limitations of we don't know exactly where we should be searching if we specify some arbitrary range. Okay. So yeah, and that's because the true bias was actually -8, which is why I said it's 7, just to highlight that point. So grid search is another technique we can use. And this is just like random search. It tries out a bunch of different values, but instead of randomly sampling them from the space, it just tries them at periodic intervals within that space. So you can see in this diagram here, they're nicely spread out. They're just tried at even intervals. Okay, so we'll implement this first function, which is going to generate a list of different parameter values, which we're going to try. So what it does is it takes in how many parameters does your model have. In our case, we have 2, the weight and the bias. How many different samples do we want? That is how many different x's here. And then what's the minimum and the maximum value, which yeah, we're not actually using that, so don't worry. Okay, so we are going to what are the parameter values which we're going to try out? We are going to so we got the number of samples that we want, then we can just do np dot uniform. No, we can do np.linspace. So between, yeah, this is where we're going to use these min-val and max-val. So this just gets us, it gets us however many we specify samples from evenly spaced within this range from min-val to max-val, n samples per underscore per ram. So basically what this first line is doing is saying, well, if we want to do, in this case, if we want to do 9 different samples, which would be this keyword argument here, well then we don't want to do np.linspace 9, because that would give us 9 different values along this space for w. In fact, we just want 3. So this line just tells you how many samples you want per parameter. So it basically takes the nth root of that, of the number of samples. But don't worry too much about that. Basically, if we wanted to do 100 different samples, then we would take the square root, because we got 2 parameters to get 10 samples per parameter, which means we take 10 different values of w and 10 different values of b, and then we would try out those 100 different values, which will cover most of this space. So we will get that linearly spaced out set of values. Then what we'll do is we will use this permutations function, which we imported from isTools. I think so. So look at what it takes in. I think that the first argument is the number of parameters which you have. Okay, the second argument is how many different parameters that you have. So, and then the first argument is a list of different possible values which can be in those sets. So in this case, we want to find every different permutation, that's what the permutations function does, of 1, 2, and 3. And how many different values should each of the permutations have? 2 in this case. So they've got 2 different values in here. In this case, here's another one where they're taking every different permutation of ABC, which has 3 values in. So then there's all the different ways of arranging them. Don't worry about it too much, but you can look that up if you want. So the different parameter values, param values there, and then the number of params is why we've passed that in. Number of params, cool. So now we've implemented this generate search grid search values. It should return us something just like this. It's going to be a list of different parameter pairs, which we're going to try out. Then we'll implement the grid search to basically go through all of these and then return the best ones. So you can see here that we're doing we're checking for each search value, parameter pair in those grid search values, which we which is what we're going to return from this and then pass into grid search as its only argument. We're going to search through all of them and then basically do what we did for random search, just see how well they do and which performs best. So we'll take the best, what do we initialize the best weights as? Well, we've got nothing so far. We haven't tried a single thing. So we'll implement the best bias and weights as none. And then we'll initialize this as infinity as well. We could just put a very high number, like 1,000,000, but this just guarantees that there's no number higher than infinity. And that's how you convert this this string inf into what's considered a very high number in Python. So for each of those search values, what we're going to do, we're going to update the model parameters with those search values. So we'll do h.update params. We'll update them with the search val. So remember, the search val is just just like a tuple of examples like this. So we want to get the first one. It's going to be the first bias we're going to try. Or weight, it doesn't really matter actually. And then the second one will be the other parameter which we're going to try. So we'll say that the search value, let's try. So we're going to set the weights to the first value in that parameter pair, which is returned from this grid search. And then we'll say the search val 1. So the second item in there is going to be the value which will update our model biases to. Okay, so then we'll make a prediction using that. So we'll use the _call method of our model defined in the linear hypothesis class above to make a prediction for the inputs we have, and then we'll use the function L, which computed our mean squared error loss between our predictions, y hat, and our labels, capital Y, to calculate how bad is this current parameterization, how bad are these search values which we're trying out at the moment. And then if the cost is less than the lowest cost we've seen so far, then we will set the lowest cost we've seen so far to what we just experienced the cost was, and then we'll set the best weights to these current weights, h.w and h.b, so the weights and biases of that model. And then once we've done that, we'll again print what's best and then return the best weights and bias. So if I run that just to define those, then here we'll actually implement it. So we're going to get the grid search values. Let's just print the first of them, so you understand that. For the first 5 of them, and then we're going to do that grid search using those grid search values to return us the best weights and best bias. Once we've done that, we'll update our model params with the best weights and best bias, and then we'll plot our hypothesis against our predictions. Our predictions and our hypothesis, same thing, against our actual data. So we're firstly going to try that for, we're just going to call it with the default. What are we going to do? Yeah, so the first one, we're going to do 100 samples. We're going to get 100 different parameter pairs from the generate grid search values. Second one, we're going to get 99, and we're going to see what the difference is there. Okay. Something like that. Cool, so here's our first 5 different parameter pairs it's going to try. So we're going to try a weight of -2.5 and a bias of 1.94, and then a weight of 2.5 and a bias of -1.38. And we're basically just going to cycle through each of those different parameter pairs and see what's best. Okay, what's the error we've got here? Unsupported operand types with non-type and float. Okay. Which of those is none? It's these, isn't it? Update param, search val 0, search val 1. Okay, so it looks like it's just returned us. Let's run this and it's printed that. So search val and grid search values, grid search. Cool. All right. I don't know quite what's happening there. So now we've got done our grid search, and it's returned these 2 different things. Okay, so we're going to set our min val and max val to set them to 10. Cool. All right. So now we can see that this is where we tried 100 different samples, and this was where we tried 99. Now, which of these is a better fit? Well, we can look at the cost. So the lowest cost was this one, 1.479. So this is meant to be a better fit than this value. Well, why is this a better fit? Because we're doing a grid search, right? It's not like it's totally random. It's this one's actually searching more. So why doesn't it have a better cost? Well, the reason behind that is actually because of the even spacing out of grid search. Now, what might happen is that the ideal parameter value is not exactly on one of these crosses. It might be right in the middle of all of them. And so the number of different grid intervals which you choose, the number of samples we define in our function, specifies, where are these x's laid out, and as that changes and the optimal parameterization stays still, it affects how close you can actually get to it. Because if we have a point in here, and this is where we're doing 9 samples, well then we're not going to get as close as we could do to this point. But if we were using say 25 samples, where we'd have 1, 2, 3, 4, 5 on each side, then we'd have a value of a weight being tried here and a value of a bias being tried here. And so in that case, we'd actually come much closer to the best parameterization, which I'm pretending would be there. So that's one of the issues which can occur with grid search as well. Okay, so now will random search and grid search get us out of the way is a question, and as you can probably guess by now of the issues I've highlighted here, they won't, and we're going to need much better optimization algorithms to help us train models to solve meaningful problems. Like, this is not really a meaningful problem. We just made a fake data set and tried to learn some simple straight line function which maps from one single value to a single output value. Whereas in reality, we want to solve problems like computer vision and all kind of much more interesting stuff, and that certainly is not as simple as this. So we'll get into that in the next notebook, but basically here you should understand this stuff and implement the code on your own. And catch up with the next notebook, which is using gradient-based optimization.